All right. Good evening, everyone. I hope my voice is audible to all of you. Okay, so we both of us, I and Akanksha, welcome you all to this course on flat slab design and detailing through CSI Safe plus manual. Okay, so we are very happy to see all of you here, all of you taking interest in joining this course. So we thank you for that, and it is a great responsibility for us to meet all your expectations during the period of this course. So we would be trying our best to give you a very good experience of learning. And with you, we will also try to learn new things because we have a very, as always, we have had in past courses also, we have a very good mix of learners that have gathered for this group. So we have students, we have some undergraduate students also. We have many of you are postgraduates. Some of you are research scholars. There are practicing consultants, professional engineers. There are people who are involved with the execution projects. Some of you are running your own companies. Uh, some of you are involved as faculty members in various educational institutes. So it is I would say, a very good mix of people that we have, and because of this good mix of learners with a very varied experience, I hope that we have a very good time during this course. Okay, so we will start with our session, and there are few instructions for you because many of you would be using Zoom, I think, for the first time. So keep your connect to the audio. Otherwise, you will not be able to listen to me. So connect to your audio. There is a button on your left bottom of the screen. So go to that place on the bottom left of your screen and connect to the audio. All right. Otherwise, you won't be able to listen to me. You connect to the audio, but you need to keep yourselves on mute because there is no purpose of you to be on unmute because it will disturb your bandwidth and it will create a problem to hearing also. So keep yourselves on mute, but connect to the meeting audio. Okay, this is one instruction. Then, as I was telling you in the evening also, that write your full name in place of your Zoom ID. Okay, so don't write some random A70, B30. Don't write names like this. Just change your name to full name so we are able to identify you. All right. And you are able to see, all of you are able to see this board. You are able to listen to me. And I hope you are able to also see the screen that I have shared. I have shared a small PPT on my screen. So I hope you are able to see all these three things. I mean, you are able to listen me, you are able to see me, plus you are able to see the shared presentation also. Okay. All right. So we will just proceed with the session. Yes, session is being recorded. We will be recording each and every session, and we would be sharing you the recorded video right after every day's class gets finished. Okay. So within an hour of our class getting finished, we would be sharing you the video. Okay. So we will start with a very general discussion today. We would try to introduce you about the topic. This is a very general discussion. Some of the elements we have already discussed during the introductory session, but just a brief recap of uh, why we are doing this flat slab course, some advantages, disadvantages. So I will just quickly run through it. Okay. So you will see that, see, some of things you may feel repeated because several students amongst you are also taking some other courses with us. Few of you are taking a morning course which we are doing on ETAP. So some part of the discussion that we would be doing, some part you will feel that it is getting repeated. But the design, see, basics of design always remain the same. So you will see some commonality between a few topics, but it's okay. It is, I mean, the design, this is the basis of design. So some things I have to uh, tell you, even if you feel it's being repeated. All right. So as we were discussing the other day, what is meant by system? Why we are talking about system? Because our name of the course is flats detailing and design of a flat slab system. Okay. So what is meant by a system? So system is a, you can say, a assembly of individual members or individual elements. So that is called a system basically. Now you will see that your structure has how many systems. You can try to figure out how many systems, broad systems in any structural building or in any structural configuration that you have. What are the broad structural systems that you can isolate? So I will say one is your horizontal system, okay, and the other is your vertical system. So you have basically two systems. One is the horizontal system and other is the vertical system. Now, what is the purpose of these individual systems? What is the purpose of these individual systems? How the load transfer is going to take place? Yes, you can write down in the chat box. I forgot to tell you how we would be operating during this session, that you can write anything in the chat box because we constantly are having a look at our chat box. So instead of, because you all are on unmute, so you won't be able to interact with us by opening your mic. So for interacting, keep writing on the chat box, and we are constantly having a look at the chat box, and it is a very good medium to communicate. All right. So I was asking that what is the general load transfer that takes place in your building systems? How is the load transfer taking place? So the load transfer takes place from your horizontal system to the vertical system and to the ground. Okay. So the first load that acts upon a general building system is, it acts upon the horizontal system. All right. And from horizontal system, it is transferred to your vertical system. And from vertical system, it gets to the substructure or the foundation system. So this is how your general load flows. Now, some examples of horizontal systems. So horizontal systems mainly include a plate-like element that we call a slab. Okay, it is a flat element which we call it as a slab. Then there is another element that is called as a beam, and then uh, these you can say are components of horizontal system. And for vertical system, you can say that you have got columns, you have got shear walls, you can have brick walls, load bearing walls. So all these are parts of your vertical system. Okay. So any structure which has to transfer its load will be transferring the load from horizontal system to vertical system and to your substructure or foundation system. All right. So the course that we are going to run about flat slab essentially forms a type of horizontal system in your building. Okay. So flat slab essentially is a part of horizontal system of your building. Now, what are the other horizontal system examples that you can give? Like one example I gave you was flat slab. What are the other RCC horizontal systems that you have come across or you have heard of? Yes, I am asking what are the other horizontal systems that you have heard of? Yes, so as Mr. Nagesh is saying, waffle slab can be an example. Okay, grid slab is one example. You have, in case of steel structural systems, deck slab arrangement is one example. Let's say we are not talking about steel structures right now. So in continuing in RCC, you can have waffle slab, you can have grid slab, you can have a conventional slab system, that is a beam slab system, normal slab, normal beam. You can have what is called as a flat slab system, or you can have a flat plate system. So These are the general horizontal systems that you come across in a building. Okay. Now the relative choice of making these systems depend on a lot of issues. Some issues are architectural issues, some issues are structural issues, some are planning related issues. Okay. Yes, folded plates. Yes, Mr. Vanch is right. One more system that can be used as a horizontal system for RCC can be a folded plate arrangement. But folded plates generally form a part of your, yes, I would say folded plate is a valid answer. So folded plate system can be one form of horizontal system that you have. Then in any, I mean, in all of these systems, you can add pre-stressing to it. So pre-stressing, I will not say uh, it is a separate system in itself. It can just be a component of all these systems. Okay, so any of the horizontal system you can strengthen it by providing pre-stressing. So I'm not putting pre-stressing in another column as such. It is just an added element for all these horizontal systems. Okay, so what were the conventional examples that we discussed? Conventional beam column, beam slab, normal beams, normal slab. We can have a grid beam slab system where our beams are closely spaced in a grid-like formation. We can have a waffle slab system where the beams are even more closely spaced. Okay. We can have a flat plate system and we can have a flat slab system also. So these are some usual examples of horizontal systems that you come across. What are examples of vertical systems? Even though I have not mentioned here, but just for the sake of discussion, what are the general examples that you come across for a vertical system? So generally you come across columns as your vertical system that is taking your load. Then you can come across shear walls that are taking your vertical load. Then you can come across load bearing confined masonry walls that can take your vertical load. Okay. Any other vertical systems that you are aware of or that you have come across? Bracings, Mr. Chirag is saying, but bracing in itself is cannot be called a vertical system independently. It generally forms a part of some other structural system. So we will not call bracing as a independent structural system. Okay. And bracings we generally do not generally provide for taking vertical loads. Yes, they may take vertical loads because of their geometry and placement, but generally they are not supposed to take or they are not intended to take vertical loads. Okay. All right. So yes, these are some examples of vertical system that come to my mind: columns, shear walls, your RCC, sorry, confined masonry walls. All these can be some examples of vertical system. All right. So we just take few pictures over here. Yes, I have taken just simple few pictures. The first picture on top left is normal slab beam system, conventional slab, where your beams are I mean, at a considerable distance and you have a slab resting on your beams. The second example that you see can be of a waffle slab. The third picture that you see, top right, can be an example of grid slab. See, grid and waffle at the end of the day, they are similar arrangements, just that for some spacings when beams are very small and very close by, you call them as a waffle slab. Otherwise, the structural concept remains the same, whether you call it a grid or you call it as a waffle. Okay. Then the bottom left picture that you see in the second row is your flat slab system. And then the last picture that you see is an example of a flat plate system. So what is the major difference between a flat slab, flat plate and your normal waffle grid and conventional slabs? What is the major difference between these systems? Between a flat slab and flat plate system and your other three systems, what is one major difference that you are seeing? That there are no beams. Okay. there are no beams in case of flat slab or a flat plate system. So it is a beamless geometry. Okay. Now, how is the general load transfer taking place in a normal conventional slab system? How is the load transfer taking place? So the load transfer path which you see is from slab to beam, and beam to column, and column to footing. Okay, that is the general load path that you have. Now, what is the load path that you have in a flat slab or a flat plate system? Because there are no beams, the load directly from slab is going to get transferred to columns. Okay, so you have one redundancy less. I mean, in the normal slabs, you had the redundancy of beams, which is absent in the case of flat slabs. So the load transfer is directly from slab to column. All right. Okay, so as I have just mentioned in the next slide, that what are flat slabs or flat plates? That they are beamless systems where your slab directly transfers its load to the columns. Now, since my slab is directly transferring its load to column, what is happening? That in the case of your normal conventional slab system, we had the load transfer going through the beams. Okay, so whatever load was coming on slabs, it was getting transferred to the beam through the shear between slab and beam, and then your load was getting transferred from beam to column through the shear in the slab. Okay, so there were two shear transfers that were taking place. One was from slab to beam through shear, and then from slab to column through shear. All right. But what is happening in this case, in case of flat slab, that load directly from slab, because there is no redundancy available of beam, load directly is going to get transferred to column. And due to this load path, there is a major issue that is observed in flat slab, which is called as, if you have heard about it, what is the major issue that you see in a flat slab system? Major design headache that we have is called as punching. Okay, so the major headache for a structural designer in a flat slab system is the issue of punching. Now, why is this punching taking place? The punching is taking place because there is no beam to transfer its load from beam to column. Okay, when there was a beam present, the loads from slab were getting transferred to the column through one-way action between beam, one-way shear between beam and column. Now, since in this case there is no beam to take that slab load, so all the slab load that directly flows into the column causes an effect that is called as punching. Okay, so if I just represent you over here. Okay, if I just represent it to you over here, let's say this is my slab element, and I am going to rest my column on this. My column is resting on this, and I am applying load from below. Okay, so what will this lead to? This is leading to this effect where my slab is getting punched through the column. Okay, so this effect where my slab gets punched through the column is called as punching. So if somebody asks you, or somebody asks me that what is my biggest cause of concern in case of a flat slab, so the biggest cause of concern in case of flat slab is the punching effect. Now, if you just see this demonstration that I'm just trying to show you, I have the slab, and earlier I was using this column in the, I mean, this was a pen, but I am representing it as a column right now. So it was punching through, the slab was getting punched through this column. Okay. Now, instead of this pen, if I am trying to use this as my column, and if I try to punch it through, you will find that I am facing a certain difficulty in punching it through. Okay. In the earlier case, my column was getting easily punched. Here, I faced a certain difficulty. Okay. Now, if I change the example once more, I take the previous column. but this time my slab is getting changed. Okay, and now if I try to punch it, I am no longer able to punch this column through this slab. All right. So through this demonstration, what we are trying to understand that in the first case, what we were doing, in the first case, what we were doing. So in the first case, I was replacing a, I was replacing a smaller cross section column with a larger cross section column. Okay. In the first case, my slab was same. I had taken the same sheet of paper to represent my slab, but it was the column size in the first case was different and in the second case was different. Okay. And then what was the second case that was happening? The second case that we were taking was that instead of taking a paper as a slab, we were taking a book, a thick book as our slab. Okay. So if I was taking a thick book, even the earlier column was not able to cause any punching in my slab. So, I mean, this is a very crude example that I'm giving you just to make you understand. So, what are the possible strategies? What are the possible strategies of countering this punching effect in a flat slab? What are the possible strategies to counter punching effect in flat slab? So, the strategies that are possible are either we provide a very big column, this is one strategy, or the second strategy is to provide a very thick slab. All right. So these are the two broad strategies that we have in front of us. One is to increase the size of the column. Second is to increase the size of the slab. Now, if we talk about the economics of a structural design, okay, if we talk about the economics of a structural design, increasing the size of the column throughout the floor is not a very economic solution. Okay, if somebody asks you to increase the size of the column for the complete story height or for the complete floor height, it does not make a lot of economic sense. Okay, so what we will do instead of increasing the column size throughout the floor height or throughout the building height, what is the economical way of doing things? That we increase the size of column locally. Okay, what is the economic solution? That we increase the size of column locally. Now, when we increase the size of column locally, what is it called in technical terms? What is this increasing of column locally called in technical terms? So this is called as, when we increase the column size locally, it is called as providing a column capital. Okay, it is called as a column capital. So what is meant by column capital? That we are increasing the size of a column locally near the slab column junction. So if you see the second picture in the slide show that you are able to see right now in the current slide, if you see the second picture, you will see that column sizes have been locally increased near the slab junction, and this type of arrangement is called a column capital. Is this understood? So this was the first strategy. This was the first strategy where we are changing our pen size. So from this lighter, smaller cross-section column, I am moving to a bigger cross-section column, but I am not increasing the cross-section throughout the length. Only at the local portion, I am increasing the cross-section. Okay. So this would be called as a column capital. Now, what is the second strategy? Second strategy was to somehow increase the thickness of slab. This was the second strategy that was available to us. So again, the same discussion that if we are increasing the slab thickness throughout our floor, it does not make a very good economic sense to increase the slab thickness throughout the floor. So what is the economic way out? What is the optimum solution that we can seek? So the optimum solution is to locally increase the slab thickness. Okay. The optimum solution that we can structurally provide is to locally increase the slab thickness, and this is called as What do we call this when we are increasing the thickness locally of a slab at the slab column junction? So we call it as drop panel. All right, or we call it as the slab drops. Is this understood to all of you? So if I just draw a picture over here, so this is my slab. If I increase the column size locally, this is my elevation that I am drawing. Okay, this we call it as a column capital. This is my column and this is my slab. So we are calling it as a column capital. So this was the first strategy that was available to us. What is the second strategy that we have? So the second strategy is to provide what is called as a drop panel. So instead of increasing the slab thickness throughout, we are increasing the slab thickness at local level near the column junction, and this will be called as a drop panel. Is this understood? Mr. Ejaz is unable to see the board. So I think you have to switch your view. You have to switch your view, I guess. Just swipe your view and I think you will be able to see the board also. Are you able to see it now? Okay. So this is the second strategy we have, is to provide drop panels where we are locally increasing the slab thickness. Okay. And the first strategy that we were talking about was to provide our column capital where we are locally increasing the column dimensions. So where do you see this column capitals being provided? Where have you seen these column capitals provided? Parking lots. Yes, in parking lots. I mean, in buildings, you see these column capitals provided. Water tanks. Yes, good observation. Mr. Yogesh has made a good observation. In water tanks, you see these column capitals being provided. Yes. Okay, so why there was some question from I think Mr. Sahas. He was asking that why uh, will not there be very high stress concentration near the slab column junction of this column capital? So yes, there of course would be high stress concentration. So to decrease our stress concentration, we are providing this slope over here. Do you see this? Why we are providing slope over here? So that the load smoothly transfers to our column. Therefore, we are providing this flared shape so that our load smoothly flows to our column. All right. So two broad strategies that you will see being used in flat slab. One is to go for column capital. One is to go for slab drops or drop panel. What can be another strategy? What can be another strategy? If let's say we do not want to go for either, we do not want to go for capital also, we don't want to go for drops also. So what can be the second strategy, or I would say the third strategy? Both. Yes, both can obviously be the third strategy where we are providing, let's say, column drop also and sorry, slab drop also and column capital also. So you will find some places where you have column capital also provided and you have drop panels also provided. Okay, so yes, there are some places where you see both column capitals and slab drops. If we do not want to go for any of these, then what can be the way out? If we don't want to go for any of these, neither drops nor capitals nor both. Yes, so one strategy, as Mr. Tejas is saying, that it can be of introducing pre-stressing. Okay. Or what can be the other strategy? That we increase the slab thickness in such a way that it takes care of all the punching that is going to develop. Okay. So instead of, let's say, providing a slab where we were going to provide drops and slab, instead of this, what do? We straight away provide one thick slab. Okay. We provide one thick slab like this so that it is able to resist all the punching that can come. Okay. So what do we call these slabs as? What we will call these slabs as? So these slabs we generally call as flat plate systems. Okay, these are usually called as flat plate system. Is this understood? Flat plate. So a general difference that you can say between a flat slab and a flat plate system is that in flat plate you have done away with the column capitals, drop, everything. You are providing a uniform thickness slab. So these we will call it as a flat plate system. Otherwise, the working or the behavior remains similar for both, but just a change in name when we are not providing any column capital or slab drop. So we will call them as flat plates. Are we okay with this? Okay, so if you just refer back to the presentation that I have shared again, so you will see on the left side, you see a column, you see a slab drop being provided. The middle picture shows you a column capital, and the third picture shows you uh, a combination of both, that is column capital plus slab drop. Mr. Tejas is asking column stress will be more for flat plate as compared to flat slab. Yes, for flat slab, your obviously punching stresses would be more because you are not increasing the thickness locally, you are not providing drop, nor you are providing capital. So stresses would be more. So generally, when you are providing flat plate systems, we have to give what is called as a punching reinforcement. Okay. What is called as a punching reinforcement, we will be giving that to resist the punching effect. We would be discussing this as we move ahead. Okay, so I hope these three strategies are clear to you. Yes, so why are these flat slabs very popular these days? This is one point that I had covered during the introductory session also. But just to reiterate, so why are these flat slab systems very popular these days? So if you see the first picture on your left, what can you make out from the picture? Can you analyze and give your viewpoints on the picture? First picture on your left. Can you just quickly summarize and tell me the analysis after looking at the first picture? So Mr. Ravindra is saying reduce story height. Mr. Chirag is saying more floor to floor height. Yes. So this is one part of the analysis. What is the second part of analysis that you can make out? One obvious analysis is that you see different floor to floor heights. Yes. What is the second part of the analysis that you can make out, which is more important? No, I mean, look at the first picture only. Just look at the first picture. Don't go to the second picture right now. Just look at the first picture. I am saying that one obvious analysis after looking at the first picture is that you are getting uh, the floor to floor heights are different. Yes, of course, that we can see. But one more critical statement is missing from what you are writing. That I want to listen. Yes, so what actually you are getting, if you just make the complete statement, I will say that for that I will say that for less floor to floor height, okay, for less floor to floor height, you are getting the same clear height in case of flat slab systems. Is this understood? I will just repeat my statement. What I am saying for uh, the what did I say? What state? What statement did I make? For yes. So for less floor to floor height, you are getting more. No, let me just rephrase it. For same clear height, you need to provide less floor to floor height in case of flat slab systems. Understood? Is this understood to all of you? I will just repeat because things got confused. I was saying that for same clear height of 2.8 meters that you are seeing in both the cases, you need to provide less floor to floor height in case of flat slab systems, whereas you need to provide greater floor to floor height in case of a slab beam system. Okay, now is this understood to all of you? So if you see what was the clear height that you were achieving in both the cases, what was the clear height that you were getting in both the cases? So you were getting 2.8 meters as your clear height in both the cases. Okay. But to achieve 2.8 meter clear height, how much floor to floor height did you need to maintain in case of a beam column system, slab beam system? How much clear height you were needed to maintain in a slab beam system? Sorry, how much floor to floor height you needed to maintain in a slab beam system? So you are needing 3.4 meters to get a clear height of 2.8 meters. Okay. And what floor to floor height do you need to maintain in a flat slab system? So you are required to maintain only 3.2 meters floor to floor height. Okay. So what is the advantage then? I mean, okay, okay, you have to provide less floor to floor height, but what is the advantage? Yes, we understood this that you need to maintain less floor to floor height, but what is the advantage? Yes, so yes, as Mr. Nagesh has said and Mr. Ravindra has said, okay, Mr. Ravindra has given us a second point, which is also valid. But what is more important point, which Mr. Nagesh is saying that you need to, let's say, okay, I will give you an example. Let's say your height restrictions, town and country planning restrictions were, let's say, 30 meters. Okay, in your case, your height restrictions were 30 meters. Okay. So what is the real advantage that you have? That in case of a flat slab building, you can accommodate more number of floors for the total height of your building. Is this understood? In case of flat slab building, you may be able to accommodate more number of floors for the same height of your building. So let's say in this example that I have just shared, how much height you are saving for each floor? How much height you are saving for each floor? So you are saving zero point 0.2 meters. Okay, you are saving 0.2 meters for each floor. So let's say in 13 floors, or in 14 floors, you get an additional story in case of a flat slab. Okay, if I construct 14 floors in normal conventional slab, I will be able to construct 15 floors in case of a flat slab with these dimensions for the total floor to floor height. So naturally, I am gaining a huge advantage of around 7 to 8% just by switching to flat slab system. Is this understood? Okay, so this is a very big advantage that we can. This is a very extremely big advantage, and especially when your real estate prices are so high, where if you are able to achieve a 7-8% additional, if you are able to create an additional 7 to 8% floor area for the same height of your building, it is a tremendous. I would say it is a tremendous profit that you are able to achieve. Okay, so therefore these flat slab systems can be extremely economically beneficial to you if you are going for a taller type of building. So Mr. Piyush is asking, but in case of flat plate system, does it work? Okay, I mean I didn't understand the question, but yes, we are talking about flat slab or flat plate. The the discussion that we are having of floor to floor height and those remain the same. Okay. So I hope you are able to appreciate this concept. What is the second advantage that you have? What is the second advantage you have? You can see in the second picture of using a flat slab system. So just try to analyze what is the second advantage of having a flat slab system by looking at the second picture. Yes, right. So as you have guessed correctly, that nowadays if you see our building is no longer only a structural architectural system. Okay, our building is no longer only about bricks and slab and beam and column, just that. Okay, nowadays there are lots and lots of services that are involved in any of the building project that you come up with. Okay, earlier days there were not so many services that used to be seen in your general buildings, but these days there are lots of services that form a part of your building system. Okay, so other than your civil structural system, you have services such as you have air conditioning lines going on, you have some water heating systems, water cooling pipes, you have plumbing pipes, you have firefighting lines going through. Okay, so there are lots of course you have the electrical cables running through. So there are lots of services that are going through your buildings. Now what happens in case of a beam? What will happen in a case of beam? So what happens in a case of beam, if I just try to explain you on a board, that in case of beams, in case of slab beam system, the beams pose a obstruction. Okay, your beams pose an obstruction in taking your service lines. Let's say I have a beam over here. Okay, so if I have to pass my service lines through it, what are my options? Either I lower down the level of my service lines. So rather than passing it over here, what I have to do, that I have to pass it below my beam. Now let's say if I am passing it below my beams, what is the disadvantage that I am having? If I am passing it below my beam, what is the disadvantage that I am facing? What is the disadvantage that I have? That I have got reduced headroom. Okay, my clear height decreases because these service lines are intruding. These service lines are intruding my clear height, and also obviously it is not aesthetically very pleasing that if you have a network of service lines going overhead, so it is obviously aesthetically not pleasing. Plus it is reducing your clear height, because generally below service lines nowadays you go for a false roofing. Okay, so you go for a false roofing So if your service lines are provided below your beams, then you are, I mean, reducing the clear height. Now, instead of going for this, if I go for such a geometry where I have these beams like this, I mean, service lines like this, and then I make a turn to my service lines, and then I take them like this, then what is the issue that we are facing? What is the issue that we are facing in this case? If we are taking our service lines like this? Yes, anyone? Right. So, as Mr. Vansh is saying that one issue is of increased connections. So, increased elbows, increased L joints, increased T joints, you have that. Plus, let's say if these are electrical lines, I'm not bothered about even taking them from the beam like this. But let's say if these are lines which are having some pressure in it, let's say these are firefighting water lines, or these are some air conditioning coolant lines, or things like that. So a sudden dip in your pipeline may disrupt your pressure calculations and all those things. Okay. So your designer for your plumbing lines or service lines may not allow such a sudden dip uh, in pressure. Okay. So therefore, this is also not a possible solution. So then what do people do? What do we do in case of beams? When we have beams and when we have to take services through them, what do we do then? What do we do? So we take them through our beams. All right. So what are we going to do? That if I had a service line like this, I will take it through, I will pass it right through my beam. Okay, so basically what I am going to do, basically I am going to cut a sleeve in my beam and I am going to pass my service lines through it. Okay, now one very valid question that has been put. Do you understand first of all this configuration? Do you understand this configuration? Do you understand this configuration of taking a sleeve through the beam? So if you see in the second picture, if you see in the second picture in the slideshow that I have just again shared, you will see that a sleeve is that a service line is passing through our beam and they have punctured our beam at two locations. Are you able to see this in the second picture? Okay, I hope you are able to see all of you in the second picture that service lines are passing through our beams and we have made sleeves in the beams and we are taking them through. Okay. Now this is not a very good solution for a number of reasons. One reason is that you are cutting your concrete from there. So in the places where you have high shear zones, cutting concrete from the high shear zones does not make a very good design sense. This is one issue. Sometimes you may also, also when you are reducing the concrete, you are reducing the compression area of your flexural member. So again, your flexural stresses are disrupted. Okay. The third issue is that many times you may cut a stirrup or you may cut a ring also when you are cutting the sleeve. So this is also not a very good issue. The third issue is that when you are making a sleeve, there is a stress concentration that is observed from where you have reduced this concrete area. Okay. So all these issues are a big headache for us when we are providing sleeves. Now, yes, as Mr. Venkatesh is saying over here, what he is saying is correct. That what is the way out if we have to, let's say, if we have to go for sleeves, let's say there is no option, but we have to provide sleeves. Okay, so what is a good way out that these sleeves can be better planned. Okay, and they can be considered in our design also. So what do I mean by better planning? By better planning, I mean that we provide sleeves in a beam along such locations where you do not need the concrete. Okay, what I am saying, we provide sleeves at such locations along the beam where you do not need the concrete in the first place. All right. So where are such locations in your beam where you do not need your concrete? If I ask you, where are such locations to be found in a beam where you do not need concrete? Yes. So one thing is in the sagging zone. When let's understand, when you are in the sagging zone, you are in the sagging zone of your beam, and at the sagging zone of your beam, let's say at the mid span, you have got your maximum sagging moment. That means you have got tension at your top. Sorry, tension at your bottom surface. Bottom face you have got tension. So below the neutral axis, somewhere near the mid span of the beam, you may plan a sleeve because concrete there is in the tension zone, and you can remove concrete from tension side because steel is taking care of the tension. Plus, at generally at the mid spans, if you see, if you do not have any secondary beam attached to your primary beam, you have a normal beam, column to column beam arrangement you have. So you will see that near the mid spans, your shear forces are also zero, very close to zero. Okay. So these two advantages you can have at a mid span of your beam. Mid span near the bottom zone, near the bottom face. So that is where you can plan your sleeves. And generally what we prefer that we plan the sleeves beforehand, before the casting. So we usually provide a GI pipe, galvanized pipe, and that pipe we incorporate during our casting. So what I am telling you, that let's say if I have this beam like this, and let's say if at all I have to provide my sleeve, so I will be providing a GI pipe here, okay, even before casting, and I will be, let's say, integrating it with my shear reinforcements, and I can provide a sleeve in such a way. Okay, is this understood? Okay, or you can provide your beams, or sorry, or you can provide your sleeves as who is suggested. Yes, as Mr. Vansh has suggested that you can try to provide your beams somewhere near the point of contraflexure in your bending moment diagram. Okay, so at the point of contraflexures, your bending moment is changing the nature. So generally you have a place where you have got no bending moment as such. So there you may try to go for a sleeve, but their shear forces are substantial. Okay, so shear forces are there substantial. So according to me, a very good place would be somewhere in the mid span, somewhere in the mid span of the beam, somewhere in the mid span where your shear forces are also very low, almost zero, and all your bending moment is sagging. So entire stress is in the tension side, which is taken by steel. Okay, all right. So these are the general locations, but this is a very ideal condition we are talking about. Okay, this is a very ideal condition we are talking about, that you will be able to plan your sleeves, and then the contractor and then the other service agencies that are involved with the service contracts would be placing all their service lines according to the sleeves that you have provided. So this is a very ideal situation and a very ideal world to live in. Okay, it does not happen in India, at least I can tell you. In general projects, nobody is going to come and ask you that they are going to provide a sleeve, or nobody is going to come and going to ask you to plan a sleeve in your beams. This does not happen. Okay, so sleeves, if you see on site, are generally cut wherever anyone feels that he or she wants to make a sleeve. They usually make a sleeve even without asking the structural engineer. Okay, so this is what generally happens in case of Indian projects. Generally, okay, I'm using the word generally. Of course, when you have good engineered projects, such things will not happen. But the general trend I'm talking about. So, how does my flat slab system help me? How does my flat slab system help me with this? So since I am providing a very thin drop like this, I am easily able to take my service lines right through this without making any level differences or without cutting any sleeves. My service lines very easily pass right through it, and then I can provide a false roofing arrangement. Okay, this can be my false roofing arrangement, and in such a way I am very easily able to manage my service lines also. So this is the second advantage, and a very I would say a very important advantage of having a flat slab system. All right, and especially in commercial structures where you see lot of services that are provided in your buildings, this flat slab system uh, proves to be very beneficial for this purpose. All right. Then what is the third advantage that you can see? What is the third advantage that you can see of a flat slab? Yes, Mr. Venkatesh is asking about, yes, so that is the disadvantage. Right now we are talking all the good things about flat slab, but then we will turn to bad things also. So then we will cover your point. All right. Okay, so what is another advantage of providing a flat slab? So flat slab systems look clean to the eye. They look pleasing because you don't have the complex networks of beams going here and there. So you have some simple geometries of drops, a simple slab being provided. So they are aesthetically pleasing to the eye. Okay, flat slab systems generally are aesthetically pleasing to the eye, and therefore they are provided. Okay, all right. So are we clear with these advantages of having flat slabs? Okay, so of course, when there are good things, then there will also be bad things. And then what are the bad things or the difficulties of providing a flat slab system? So the biggest, I would say, difficulty or disadvantage of a flat slab system is very low resistance to lateral loads. Okay, the biggest disadvantage of providing a flat slab system is a low resistance to lateral loads or earthquake loads. Now, why the resistance is low? Can anyone tell me why resistance is low in case of a flat slab system? Yes, why resistance to earthquake is low in case of flat slab systems? So, as Mr. Razi is rightly saying that when you have a normal slab beam column system, the lateral load generally flows from slab, then from slab it is transferred to your beam, and from beam, my beam column together form what is called as a frame action, and through that frame action, my lateral load is transferred from from beam to column. Okay, so this is how my load transfer takes place in a typical slab beam column system. That slab first transfers its load to the beam, and then there is a frame action between my beam and column, portal action you can say. So that portal action transfers the load from beam to column. So so having a slab beam column system is a very robust system to resist lateral loads. Okay, it is a very robust system. But now what happens in case of a flat slab system? You have slabs directly resting on your columns, and those are very thin elements that you have. Slab elements are very thin. Those are resting on your columns. And when lateral load comes, the load transfer that was the system or the load path that was getting generated between a beam column system is not generated over here so effectively. Okay. So you are not able to effectively generate a good load path to transfer your lateral loads. All right. If you have heard about the capacity design method, or if you have heard where your yielding takes place in a system, in a structural system, generally you will see that in a slab beam column system, our plastic hinges, or what we call as the mechanism, takes place at the beam, in the beams. Okay, your mechanisms or plastic hinges, they form at the beam locations in case of your slab beam column system. But in case of a flat slab system, they are usually formed at the slab column junction. Okay, because there is no redundancy of the beam or no stiffness of the beam available. So generally the plastic hinges are formed at slab column junction. And this makes it a very unstable system against the lateral loads. Is this understood? This makes it a very unstable system against the lateral loads. Okay. So if my slab column system that I am providing in flat slab is not able to resist lateral loads, then what I have to do? What I have to do if my slab column system, flat slab system, is not able to take lateral loads effectively, what do I do then? Yes, anyone? What do we do? What do we do? That we have to provide an additional system to take care of lateral loads, which is generally provided in the form of a shear wall system. Okay. So what I'm trying to tell you, that when we have a flat slab system, when we are using a flat slab system, it is not enough. The flat slab system is not enough on its own to take lateral loads. It is only good enough to take your gravity loads. Okay. To take care of the lateral loads, we have to introduce another system, which is called as the shear wall system. Understood? So you have to have two systems in case of flat slab to take care of lateral and gravity. So your slab column system will take care of your gravity loads. Your shear wall system will take care of your lateral loads. Whereas when you are having your normal slab beam column system or the frame system was sufficient or capable enough of taking lateral loads as well as gravity loads. Okay, it in itself was capable of taking both the gravity and lateral. But in case of flat slabs, it is not able to take lateral loads. It is good for taking gravity loads, but it is not able to take lateral loads sufficiently. So you have to introduce another system in the form of shear walls. Is this understood? So this is, I would say, this is a big disadvantage that we have, and this leads to lot of flat slab buildings right now being done without proper engineering. Okay, this leads to the issue that lots of flat slab buildings nowadays are being done without proper engineering. Why they are not being properly engineered? Because for gravity loads, we understand the issues, we design it accordingly. But the lateral load issues, we do not understand it properly. And the placement of shear walls that we give, or the shear wall locations, or the forces on shear walls that we calculate, those are not done with a proper understanding. And lots of design errors we commit when we are providing a flat slab system with shear walls. Okay. Usually, if you check the design, let's say if I'm talking about Indore, I would say 8 out of 10 buildings are not properly designed for 8 out of 10 flat slab buildings in Indore are not properly designed to take lateral loads. Okay. So this is a very big issue when you are designing flat slab systems for earthquake loads. Is this understood? Okay. Now, even if you are providing lateral load resisting system in the form of shear wall, let's say even you have provided good shear walls and everything, still when your flat slab building undergoes earthquake loading, or it takes earthquake load, what will happen? That your punching effect becomes even more critical. Okay. Even if you have provided proper shear walls and properly you have made it earthquake resistant, still in case of earthquake loads, lateral loads, your punching effects become even more critical for us. So you have to you have to take care of punching even more. Okay, that entire thing becomes even more critical for us to design. So this is the another difficulty that we face when we are providing flat slab systems. So flat slab systems, I will say, are not very good systems to be provided in high seismic zones. They are not good systems. Even if you are even if you are providing shear walls, still the inherent disadvantage of flat slab is that it is not a very good system for high seismic zones. All right, and in high seismic zones, going to a very great height, flat slab systems are not for you. Okay. Then a general difficulty I would say in flat slab system is that you do not have good manual methods available to design a flat slab system. But see, this is no longer a difficulty because anyway we have good softwares these days which we can very conveniently use to get proper results. But uh, but uh, there are practical behavioral challenges that you face when you are designing a flat slab system, that the behavior understanding of behavior is generally not sufficient while doing a flat slab system. All right, so these are the general difficulties that you face. Mr. Venkatesh is asking, most of the tall buildings are in flat slabs in metropolitan cities. Okay, I think he's not asking, he's telling. All right, so
He's asking why. नहीं why मतलब metropolitan cities में जो high है तो भी वो provide करें.
okay, are you asking or are you stating? I'm not sure whether you are asking or you are stating for a fact. Asking, very good. So he is asking that most of the tall buildings are in flat slabs in metropolitan cities. Yes, I mean, my statement did not mean that you are not allowed to provide flat slab systems uh, in tall structures. But if you refer to IS 16700, there is a limitation that is provided, or there is a limitation that has been imposed upon you for the height of a building which you can construct in a flat slab. Okay. Uh, See, our codes are not denying the use of flat slab. They have just made the use uh, subject to very stringent criteria. If you read, if you read the latest code IS 1893 2016, they have asked to do a non-linear analysis of your flat slab system. All right, they have asked to perform a non-linear analysis for your flat slab systems for designing them in earthquake loads. Okay, now we are not, our structural engineers are not very good with the equivalent static method also. Okay, and the code is asking us to go for a non-linear analysis. And even the code, people are not sure, even we are not sure how we are to go for a non-linear analysis. There are lots and lots of practical difficulties that are present in performing a non-linear analysis. There are material difficulties, how to define the material properties, how to define the stiffness properties. There are lots of difficulties. So if you read the code IS 1893 2016, if it is telling you to do non-linear analysis and it is not telling us how to do this non-linear analysis, in a way, maybe they do not want us to provide flat slabs, or I don't know why they have made these criteria very strict as such. So even, I mean, forget the issue that you are not going for non-linear analysis for a moment, but you may provide flat slab buildings with shear wall to a considerable height. But what I was trying to tell you, that the inherent disadvantage of flat slab still remains. See, uh, you can design, that does not mean that it is a structurally a very efficient system. Okay, so flat slab system under earthquake loads is not a structurally efficient system. This is what I'm trying to tell you. Yes, I think I will have to read it. But zone 3 and above flat slab systems, if you are providing, you need to do a very rigorous non-linear analysis in case you want to provide. And these flat slab systems have been only included in the new code. I mean, in the IS 1893 2016 code, they have just been recently introduced. Otherwise, for all these years, we did not have a flat slab system in our earthquake code. So they have included the flat slab system because of the gaining and rising popularity of flat slabs. But there are lots of rigorous analysis that your code is asking for you to perform, which even the code has not told us how to perform. Okay. I'm not sure whether code has, I don't think code has said no to flat slab in zone 5. I'm not sure it has said so, but it has imposed severe restrictions, analysis restrictions, if you intend to provide a flat slab system. All right. Okay. So, Mr. Ejaz is asking, can flat slab system be used in structure design with long column? Yes, I mean, with long column you can combine your flat slab system. There is no, I mean, if everything is properly taken care of, there is no such issue as such that you cannot provide long columns with flat slab. Okay, so a very general discussion that I usually always have whenever I take a design course. So uh, when I say a process of design, what does my process of design mean? What is my objective of carrying out this design process? What are my intended outcomes if I ask you? What are the intended outcome or what is my objective of doing a design? So when I say that I want to design this, what all things do I want? Yes, I mean, you can answer in the chat box. It is a pretty general discussion that we are having. When I say that I am supposed to design this, what actually I mean, what are my final objectives or final outcomes that I'm looking at? Yes, I mean, this is a very general discussion. We have had this discussion in the morning session also, but just for repeating it, what our final what are our outcomes, that we need to have sizes of concrete element. This is our first objective. Okay, I want the size of concrete element. I want the size of slab. I want the size of drop. I want the size of column capital. I want every size to be finalized. Then I need what? I need the reinforcement. Okay. I need to find out what amount of reinforcement is required. What is the number of bars, 16 mm dia or 12 mm dia or 10 mm dia? What is the spacing that I need to provide? Okay. So 12, 200 mm spacing or 100 mm spacing, or I mean, I need to find out all the details of reinforcement. And then I also need to know about the placement of my reinforcement. Okay. Or I will say I also need to finalize my detailing. So what do I mean by placement? That whether the steel I need to put at the top or I need to put at the bottom or I need to provide at the sides or I need to provide in the form of links or I need to provide them in the form of straight bars, bent up bars. So these all are about placement and detailing. Okay. So whenever I say that I want to design this, basically I am meaning that I want to find out these three things. Okay. I hope, I mean, this is a very general discussion that we are having. So this is my expected outcome or expected or the objectives with which I am taking a design process. All right. I hope you are able to understand this. Okay. So now my next question is that what do you what are the procedure, what is the procedure, or what are the steps do you follow when you have to achieve this? This is your final outcome. Okay. So what are the steps that you would be following to have this outcome? What are the steps that you will follow to have this desired outcome of design? So I will say that first, my first step would be, I'm talking more about a computer aided design process right now. I'm talking about a computer aided design process where we are going to use some computer software. So my first process will be to create a computer model. Okay, this will be my first process, or I would say this would be my first step to create a computer model. And my computer model will be such that it represents the actual configuration that I'm going to provide. All right. So this will be my first step. What will be my second step? Once I have a computer model ready with me, what will be my second step? So my second step would be to provide loading. Okay. So loading means that I will apply whatever the loading that is expected to come on my structure. Okay. It may be dead load, it may be live load, it may be wind load, earthquake load, whatever expected loads the structure design live. I will try to put all those loads in my computer model. All right. So these two, I would call that these two are inputs that we have. These two are the inputs. These are the things that we are giving to our computer software. In this case, we are going to use safe. So these are the inputs. Then on the basis of this, what will be the output? So I will say the first output will be the analysis results. Okay, so Mr. Piyush has had a very long question he has asked. Okay, so I will try to answer your question when I am able to read it because it is a pretty long question that I am able to see from here. So we will come to your question just a little while later. Okay. So coming back to this discussion, we first created a 3D model, then we uh, applied loadings uh, which was I mean which reflected the actual loadings that were coming to act on your structure. Then what would be the third step? Third step would be that we would be carrying out analysis. So by carrying out analysis, I mean that I would be getting bending moments, I would be getting shear forces, I would be getting compressions, tensions, torsion, all those actions, deflections, all these actions I will be getting, and my computer would be internally solving me to give me all these analysis results. Okay. Once I have my analysis results with me, then I can take these analysis results and proceed to design. Okay. And of course, by design, what I mean to finalize the RC sizes, to find out the reinforcement, okay, and then to find out the placement plus layout. All right. So these would be then my expected uh, outcomes of carrying a design process. So are we clear with these steps that we have to follow? Are we clear with these steps to follow? Okay, so these are very generalized steps. I mean, there is nothing very unique that I have told you. These are the usual steps that even if you do not know in this sequence, you have been following this in the same order, even if you are not aware. So this is not a very uh, technically expert discussion that we are having. Just a routine thing that I am trying to tell you. So we will create a computer model, then we will go for loadings, then we will go for the analysis. On the basis of analysis results, we will go for design. By designing, I mean that we would be finalizing the sizes, we would be finding out the reinforcement, and we would be deciding the placement and layout. Okay. Okay. Now coming back to the slide that I was just showing you. So if you are able to see this slide once more, so you see that I have written a statement that design is an iterative process. Okay, I have written this statement that design is an iterative process. What does this statement mean? You may write in the chat box. I am asking that what is implied by this statement when I say that design is an iterative process. Just write in the chat box. Yes, so what is meant by a trial and error? Basically, iteration means trial and error. Okay. So what does iterative process mean? That you have to go for a trial and error process. So where is the trial and error happening? Can anybody of you point out? In which step is the trial and error taking place? Mr. Nagesh is saying in the analysis, trial and error is taking place. But I do not agree. Analysis is not trial and error. Analysis is pure mathematics. So trial and error is taking place at, as Mr. Tejas has written, at the level of size selection. Okay. So where is my trial and error taking place? That when I select a size, okay, why I need to select a size? Why I need to select a size? Because unless I do not select a size, there would not be any stiffnesses that my analysis can take into account. And if there are no stiffnesses, there is no stiffness matrix that can be formed. So there is no analysis. Okay. If there are no stiffnesses that are defined, there is no analysis. If there is no analysis, there is no design. So we have to have some basic sizes if we are to perform analysis. Okay. Now this is called as a catch-22 situation. What this situation is called as? This situation is typically called as a catch-22 situation. What does it mean? That your output, what was your output? Your output was finalizing the sizes. So this was your output, but you are being asked to give this as your input. Understood? So what was your expected output? You are being told that you have to provide this as an input. So this is what is called as a catch-22 situation. So how to get out of it? How to get out of it is to start by providing some assumed sizes. Okay. The way out is to provide some assumed sizes. So this is where some basic codal provisions or some basic thumb rules or some basic code criteria come to help us. All right. So what is the iterative process that we are going to follow? That we are going to start with some assumed sizes. Okay. So I will start with having some assumed size. So I write that this is my assumed size. Okay. This is my assumed size. This may be based on my code provisions. Okay. Or some minimum criteria. or some thumb rules. There may be some code provisions that you have to provide some minimum size like this. Let's say our code tells that you have to provide a minimum beam width of 200 mm, or let's say our code says that you have to provide a minimum slab thickness of 125 mm, let's say, for example. So you have to start with some codal provisions that are given to you, or some minimum criteria, or some thumb rules that are available to you. So this is your starting point. Okay, this is your starting point. Then you go for analysis. Okay, and then you perform the design step, and then you check these sizes, which you have assumed in step 1. So you check these sizes assumed in step 1. All right. If these sizes are found to be okay, you may go for reinforcement calculation, plus you may go for placement and layout, and your process would be complete. Okay. If these sizes that you had assumed in 1 are not found to be sufficient, then you go back to your uh, first step. You again choose some sizes, you again go for the analysis, again go for the design. So therefore this process is called as an iterative process. Is this understood? Why we are calling it as an iterative process? So design is never a straight line process. It is always the loop process where you start from a point, you reach this. If it is not good, you go back. So this is a loop that you have to be in, and this is called as an iterative process. So the final aim of your design, or as a structural engineer, our aim is to provide an optimum solution. Okay, what is our aim? Our aim is to provide optimum solution in such a way that our structure is uh, our structure has sufficient strength as well as sufficient stiffness as well as sufficient serviceability. So what I'm saying, that my aim is to provide optimum structure. Okay, I'm not saying that I'm going to provide a very high cross section, or I'm going to provide a very low cross section. I'm going to provide a very optimum section. Optimum means it is just right. Okay, it is neither too big, neither too small. It is just right. All right, and in such a way that it is able to take the strength. So it is strong enough also, and it is serviceable also. Okay. So whenever we are designing, we have to design in such a way that it is optimum solution, and in addition to being optimum, it exhibits proper strength, and it exhibits proper serviceability during the design life. I hope you understand. These are some very basic discussions that we are having. You may have studied at various levels these all aspects, but just to build a platform for our course, we are discussing these basic uh, things. So in strength, what are the issues that you would be checking with respect to a flat slab system? Right now I am talking about what are the issues that I would be checking with respect to the strength criteria. So I would be checking, I will say, for strength, I will check punching. This is my major headache. I will check punching shear. I will check what is called as one-way shear. Okay. I will check flexure, and generally there is no torsion as such, but I will check torsion also. So these are the major actions that I will check my flat slab for the strength criteria. So it is punching, it is one-way shear, it is flexure, and then there is an issue of torsion. Okay. Then what are the serviceability criteria that we would be checking. So the very important serviceability criteria that we would be checking for RCC is deflection. Okay. So this would be the serviceability criteria that we would be checking our structure for. Is this understood? Is this understood to everyone? Okay, so this is how we are going to proceed. That finally, when I say that I have designed, I will be finding out the optimum cross section sizes. I will be trying to find out the reinforcement, and I will be trying to find out the reinforcement placement and arrangement, and we would be finding our optimum sizes in such a way that it is able to provide proper strength in a way that it is able to take all these actions, and plus it is serviceable by having deflections within the permissible limits. Okay, so these are all the factors, all the parameters that we would be discussing. Okay, so I think we will stop here for today's session. We have discussed number of things. So tomorrow when we meet, what we would be going to do, that we would be starting with the first process of our design, that was the modeling process or the modeling step, and we would be starting with modeling. And since we are going to use software, so we would be starting with SAFE, CSI SAFE. So we would be first introducing SAFE, we would be taking a walkthrough of SAFE, and then we would be discussing the steps to create a computer model in our SAFE program, SAFE software, I would say. So basically, we would be starting with the step of modeling when we come tomorrow. Okay, so this is going to be our first step when we come tomorrow at 7:30. All right. So I think we will stop here, and what I will do, that I will just move to my laptop. I will switch off this mobile from here, and we will take your questions, because there were few questions that I think are unanswered. So we will take your questions now. Okay, so I'll just switch off my mobile and go to the laptop. Hello. Yes, is my voice audible to all of you? Okay. Yes, so generally this would be the pattern of our sessions, that we would be having our discussions first, and then we would be switching to question answer session at end of uh, every session every day. Okay, so generally typically our question answer sessions go around for usually 10-15 minutes. So if someone is in hurry, he or she may leave after our daily discussions are over, because after that, when we are taking question answer sessions, we generally do not discuss anything new. All right. Yes. So do we have questions? If I have missed any question earlier, you may just repeat it once more. If I have happened to miss any question, you may repeat it once more. Mr. Razi is asking an interesting question. He is saying that is there much use of providing flat slab system in precast RCC building? So I think more than use, your question should have been that whether it is being provided or not. I mean, uh, yes. So to that, I would say that I have not seen them being provided as of now. But of course, I will say that precast, just like pre-engineered buildings that you have in steel construction, are the way ahead because of the obvious advantages of maintaining good quality and of less labor intensive. So of course, all the advantages that you have of precast are, I mean, all the advantages that you have for pre-engineered steel construction are the same as we have for precast flat slab systems also. But to my knowledge, I have not actually seen any precast building. But there can be. I mean, I see no issue why there should not be a precast system as such. Mr. Tejas is asking, I have seen precast flat slab and column. They tend to give small column section as compared to regular flat slab. No, I mean, Mr. Tejas, you cannot make such a general comment because it depends on lot of things. What is your concrete grade that you are using? Because generally you go for high grade concrete when you are using precast construction. So I think you cannot make such a general comment. You have to go in the design aspect to to find out more about the sizes. So I will not be commenting on this. Yes. Do we have more questions? Okay, I think there are no questions. Yes, I think today is the first day, so you may not be having many questions as such because we have not started with anything substantial till now. And I think Akanksha has given a lot of answers uh, to personal questions till now. So Mr. Rajesh is asking, although he is asking me privately, but still, can concrete grade depend on flat slab? I mean, I did not understand the question. Can concrete grade depend on flat slab? Okay, so generally, if you see, due to the thickness restrictions that we have, and due to the punching that is critical to us, generally you will see that in flat slab constructions, we tend to go for a higher grade concrete. Why we are going to go for a higher grade concrete? That is because we need to increase the punching resistance of our concrete material. So generally, as compared to a normal constructions, yes, people do try to go for a higher grade concrete. Okay. Mr. Piyush is asking, Mr. Piyush is asking, can we give cantilever flat slab? And second question is, flat slab is one way or two way? Yes, it is a good question. So see, flat slab one way, two way will basically depend upon the aspect ratio that you have. That is the LY and LX ratio. It will generally depend on that. So yes, flat slab can be one way or two way depending on the aspect ratio. And the second question was whether flat slab can be cantilever. So yes, flat slab can also be cantilever. I mean, you must understand that flat slab is just like any other slab. Just the difference is that it does not have beams. So obviously there would be some problems that you would face in providing a cantilever slab, but there is nothing like you cannot provide it. So of course you can provide. And to the question whether flat slab will be one way or two way, it will depend on the aspect ratio. Mr. Sahas is asking, can you explain the lateral load transfer once again? Yes, I was trying to explain you that in case of normal slab beam column system, our load is earthquake load first uh, is I would say first hits our slab, because that is where your entire live load is concentrated. So earthquake being an inertial load, the first action that earthquake loads create is at the slab level. Okay. Now from the slab level, your slab, the force gets transferred to your beam. So the beam undergoes your movement, and from your beam, due to the portal action between beam and column, the movement is transferred to your columns. Okay. Generally in the form of axial loads mainly. So beam is an important and a critical element that is available in case of a frame structure to transfer your lateral loads to columns. All right. But when you are having your flat slab systems, your slab thicknesses are generally low, and then there is not a rigid element, or there is not a robust element, stiff element that was present in case of beams, uh, present in case of flat slabs. Okay. So due to this, the load transfer is not proper, and therefore if you see, the plastic hinge formation may take place at the slab column junction in case of flat slabs, and you don't have much means to avoid this action happening. So this is a very critical action where your plastic hinges may be formed at slab column junction, because then your columns may they may undergo a very high story deflections, lateral deflections. So therefore, this system is not very good in itself to take lateral loads, and therefore you have to introduce some other lateral load resisting system, generally in the form of shear walls. Mr. Piyush is asking, in this course, are we going to cover shear wall? Means without shear wall, it's not compatible to take earthquake loads? Yes. So we would be taking shear walls, but we would not be discussing on how to design the shear wall, or we would not be discussing on how to finalize a position for shear wall. So we would be taking shear walls for gravity design, but that is where we stop. We would not be going to the issue of designing shear wall for earthquake loads, or trying to figure out a configuration of shear walls for earthquake loads, because then we have to understand a lot of things about earthquake loads to finalize this. All right. Mr. Chirag is saying, how does the behavior change when peripheral beams are also provided in flat slab system? Yes, very good question. So I will be answering your question when we maybe tomorrow or day after. But providing edge beams or providing peripheral beams is a I would say is a good way of minimizing the deflections in our exterior panel, and it is also a good way of reducing the punching effects in our peripheral columns. So generally we do provide peripheral beams with flat slab systems. I would be talking more on that as we proceed, maybe in day after tomorrow's class. Yes, and one more advantage of providing edge beams is that it helps in resisting the torsional effect at the slab edges. So Mr. Chitarth is asking, shall we use mixed beam slab system and flat slab system in one story? Yes, you can use. There is no restriction as such. You may use some places you may provide beam column, some places you may just go for flat slab. So in one story you can mix and match. I mean, there is no restriction as such. Mr. Sahas is asking, just like we have strong column, weak beam philosophy in general building case, do we have such philosophy for flat slabs? Yes, so that was what I was trying to tell you. You may not be able to, even if you want to have such a philosophy, you cannot ensure that such a philosophy actually takes place in real action, because what is going to happen is that your slab elements are very weak as compared to the column stiffnesses. So even if you try to avoid it, still you will see that the hinge formation or the plastic failure takes place at the slab column junction. So unless we do not have shear walls introduced, this system is very poor in lateral loads. A very interesting question asked by Mr. Razi. He is asking, can shear reinforcement be provided in flat slab just like hidden beams? Yes. So I think if you had attended the introductory session, I was discussing one issue with you, that in case of flat slabs, I mean, I do not know how many of you are aware with this, but let's say in Indian code, we have, for ductile design, we have what is called as a special movement frame. Okay, I don't know how many of you are aware. This is a slightly advanced discussion that we are having. Those who are doing their postgraduate studies and all that, they may be aware of these issues. So in in frames, actually we have what is called as a special movement resisting frame. Okay, that is designed to exhibit uh, ductility. I hope you are aware. And one frame you have is of ordinary movement frame. So ordinary movement frame means that which is not designed as per IS 13920, and it will not exhibit ductility. Okay. So that's all we have in Indian code. But if you go to American code ACI 318, they have another system that is called as an intermediate movement frame. Okay. So it is in between the special movement frame and the ordinary movement frame. So intermediate movement frame has intermediate levels of ductility available in it. So special movement frame was having very high ductility. Ordinary movement frame was having almost no ductility. So this intermediate system has intermediate levels of ductility. Okay. So the interesting thing which I want to tell you is that American code gives gives this intermediate movement frame system in case of slab without beams. Okay. So in case of slab without beams, you have an option of designing it as an intermediate movement frame system. So what do we understand by slab without beams? So slab without beams basically mean our flat slabs. So you have this extra option available in case of American codes to design a frame as intermediate movement frame, so that it will exhibit some intermediate level of ductility. So what is the basic concept there? That they try to reinforce, as you just mentioned, they try to reinforce the column strip areas. I will tell you what is column strip, what is middle strip. So the portions between the columns, those portions they try to reinforce by providing some extra reinforcement, by providing some extra shear reinforcement. So that is the concept that you are trying to tell here. So we would be discussing it. I have added that topic from this course, from this series of what to say, from this season of the course. What do they say nowadays? Yes, from this season. So I have added this issue of intermediate movement frame from this course onwards. So I would be just telling you about the detailing aspects. I would be not going into the design aspects, but we would only be telling about the detailing aspects. I have seen, Mr. Chirag is saying, I have seen engineers provide flat slab with periphery beams in higher seismic zones. Does code comment on this type of behavior? No, so that was what I was trying to tell you. Flat slab are allowed in higher seismic zones, but only flat slabs are not allowed. You have to couple your flat slabs with shear wall systems. So providing edge beams or not providing edge beams does not make difference. Whether you are providing properly designed shear walls is what is important. We answered it. So yes, providing only peripheral beams will not help you in will not help you in providing frame action as such. So you have to couple your flat slab system with shear walls. Mr. Piyush is asking, what is PT slab? Is it same or different? So PT slab means that you are just trying to strengthen your slab or whatever. If you are providing PT system in your beam, you are trying to create some pre-stressing in your element before it starts taking load. So that is the basic concept of a PT. You are pre-stressing it before it starts taking external loads. So it is different. Of course, I will say that the system is same, flat slab system remains the same, but you have added an additional element of pre-stressing to it. Yes, any more questions we have? Okay, so I think we have no questions. So then we will, no. Okay, so we will stop here then. So have a good day. No, so day is almost, I think, over. So have a good night, everyone, and have a good day tomorrow. So tomorrow happens to be Engineers Day. So I will wish you uh, a good Engineers Day, everyone. So tomorrow, I think you know why we celebrate Engineers Day. Are you aware why we celebrate Engineers Day? Yes, so Mr. Swapnil is aware. In the meanwhile, Mr. Rajesh is asking flat slab level may be up and down. So I think by up and down level, you mean that whether you can create level differences in a simple flat slab system. So generally, if you are not providing beams, then it becomes difficult to create a slab differences in your flat slab because of the break in continuity that takes place. So if you are needing to provide level differences in your flat slab, then you have to have beams where you are creating this level difference. Okay. All right. So yes. So Engineers Day we celebrate it as a I think birth. Is it birthday? Yes, it is birthday of Sir Mokshagundam Vishweshwaraya. So he was a great engineer and he designed lots of hydro projects in India, across India. And yes, he was civil engineer, of course. Acha, haan, tomorrow is Engineers Day. So Engineers Day can be for any engineer. But yes, he was a civil engineer. See, in earlier times, engineer used to mean civil engineer. Okay, I mean, all these branches have come very late, I would say. Your engineers used to mean civil engineer or mechanical engineer, but engineers used to mean civil engineers, right? Yes, and earlier they used to be employed by the army, British army or the armed forces. They used to have an engineers group, engineers corps, and he was from COEP, as Mr. Sahas is adding. So COEP is the second oldest college of South Asia, I would say. The oldest being IIT Roorkee at Roorkee, which started as a Thompson's College of Civil Engineering. Anyway, so yes, so tomorrow we celebrate his birthday. So yes, so we being civil engineers ourselves, it is a proud thing that it is a civil engineer's birthday, which is marked as an engineer's day. So yes, Mr. Aziz saying civil engineer means public engineer, right? So I mean, he has put a question mark after that. I don't know why the question mark is. So civil engineering, I would say, is the closest that you can have to public service because whatever projects we do are usually of great importance for the general public. Whether we are doing uh, sewage projects, whether we are doing freshwater projects, we are doing road projects, we are doing building projects, they are generally for the use of the common public. So civil engineering is most closely associated with the general public well-being. All right. So we have a great responsibility as civil engineers to take our nation ahead. And as we are progressing ahead, we are in need of even more infrastructural developments. Even more infrastructure needs to be built, and that is where civil engineers have a big role to play. Okay, so right, I think with this, yes, as Mr. Piyush is adding that Vishweshwaraya, Sir Vishweshwaraya was later made as a Diwan in Mysore, equivalent to the chief minister. And yes, I would say because I am from Indore, so we have a hydro structure called as the Yashwant Sagar, where we artificially stop water. So that Yashwant Sagar project was designed by Sir Vishweshwaraya. So our city Indore has a live project designed by him. Okay, so we are fortunate enough to be having a project designed by him. All right. Okay, so yes, we will stop here, and tomorrow we will again meet uh, at 7:30 evening. Okay, good night, everyone. Have a good day. No, have a good night, whatever is left. See you tomorrow. Bye bye.